Good day. For those of you who do not know me, my name is Douglas Harder, and in this topic, we're going to discuss the superposition principle and understand why we are dealing with linear maps and linear operators. So in this topic, we will describe the superposition principle, give some examples, and examine the need for functions that preserve vector space operations. So, from Wikipedia, the superposition principle is an observation from physics that there are many systems where the net response at a given place and time caused by two or more stimuli is the sum of the response that would have been caused by each stimulus individually. So here we see an image that shows the superposition of waves. So there are larger waves, and superimposed upon those are the smaller waves created by the duck and the even smaller waves created by the ducklings. Now, one interesting observation is there is a specific single wave called a soliton that does not obey the superposition principle when two such waves meet. However, this is the exception, not the general rule. For example, here on the top left, we see a middle C being played. On the top right is white noise. Now, when we add the noise to the middle C, we now hear, together with that middle C, the noise. One of the goals of sound engineering is to remove noise. So, for example, the goal of noise-canceling headphones is to estimate the noise vector U. So in the image here, in the top left, we see the actual noise produced by the background environment. In the top right, we see the sound that the earphones are intended to produce, in this case, a simple middle C. If we can estimate the noise vector U, we can then calculate the negation of the noise vector and then add that to the sound that is being generated by the headphones. So now the headphones are actually going to produce not only C, but also the negated noise. However, when you now play that music, when it is combined with the actual noise coming from outside the outside environment, the noise and its negation cancel each other out, and all you hear is the sound that was intended to be produced, that is, in this case, a middle C. The gravitational and electromagnetic forces also obey the superposition principle. The force on an object exerted by multiple different objects through gravity is equal to the sum of the individual forces on that object. The same is true for the electromagnetic force. Also, alternating current, that is, sinusoidal currents, in a circuit that has resistors, inductors, and capacitors displays a vector-like behavior. If you double the current, the voltage response will double. This is essentially scalar multiplication. If you add two currents and put the sum of those two currents through the circuit, the voltage response of the circuit is the sum of the individual responses. That is vector addition. So engineers therefore do prefer to work with mappings that preserve vector space operations. So the response to a sum of inputs should be the sum of the responses to the individual inputs, and the response to attenuated or amplified input should be the response similarly attenuated or amplified. Attenuated generally is the term used for a scalar multiple where the scalar is less than 1 in absolute value, and amplification is when the scalar is greater than 1 in absolute value. For example, suppose you develop a sound system that nearly eliminates white noise, however, leaves the voices of humans essentially unchanged. Then, when you mix white noise with human voices, the noise should still be eliminated while the human voices should remain unchanged. So consequently, we are going to be looking at functions that behave as follows. We are going to look at all functions that, when applied to a linear combination of vectors, is equal to that same linear combination of the function applied to each of the vectors. Now, interestingly enough, you've already seen one of these. You've been working with it for 2 months now. In fact, if you saw it in high school, you've been working with it even longer. The derivative. The derivative of a linear combination of functions is that same linear combination of the derivative applied to each of the functions. So this is actually a very specific example of one linear operator. Well, this entire course from here on in is going to be devoted to examining the properties of linear maps and operators in general. And interestingly enough, we will see therefore that many of the properties that we will deduce, if not all, also apply to, for example, the derivative. So, following this topic, you now know that the superposition principle comes from natural phenomena. You understand that these phenomena can be described through vector space operations. You now can see the potential for the need for functions or operators and mappings that preserve vector space operations. That is, the response to a linear combination of inputs is that same linear combination of the individual responses. Here are the references, acknowledgements, the colophon, and a disclaimer. Cheers!